So I welcome you once again to the video session where we are actually been discussing about the radiation mode of heat transfer. Already two videos have been discussed in detail. So those who are new to this particular channel, you can check out the links which has been given in the description. Make use of those two links where I have discussed few concepts related to the basics of radiation and also about the resistances associated with radiation mode of heat transfer existing between two bodies. And this is a question which has been asked in the engineering services in the year 1994. So you all know that calculator usage is not been allowed over there, but still some certain amount of problems do exist in the question papers. So we'll just start discussing about this question. What is the net radiant interchange per square meter for two very large plates at the temperature of 800 Kelvin and 500 Kelvin respectively? The emissivities of hot and cold plates are 0.8 and 0.6. So you know that two temperatures have been given for two different plates, and one is of 800 Kelvin and this should be your hot body or hot plate, and next one is comparatively low of 500 Kelvin and compared to the first one, so this should be your cold plate, and their corresponding emissivities have been given because they are not going to be a perfect black body, which means all the energy present in it is not going to be radiated in an effective way. There will be some resistance associated, and that is surface resistance, which has been clearly explained in the previous video. And the emissivity of the first plate has been given as 0.8, which will be denoted as emissive epsilon 1, and the second plate emissivity is also been given, which is epsilon 2, and these temperatures will be taken in order as T1 Kelvin and T2 Kelvin, right? Okay, and Stefan Boltzman constant you have to remember, and it will be usually denoted by sigma, and its value is very easy to remember, 5.67 into 10 power minus 8. Sorry for this. So it is 5678. You can remember in this way, but it is minus 8, right? Okay, so these are all the options which has been given for this particular question. Option A, 1.026 kilowatt per meter square. Option B, 10.26 kilowatt per meter square. And option C, it is 102.6 kilowatt per meter square. And option D, 1026 kilowatt per meter square. So first we can find out the answer in watts per meter square, and then let us convert the final answer into kilowatt. So I'll just explain you how to proceed on with this problem. Let us try to take the two plates. First of all, whatever been given in the question, try to convert that into a diagrammatic representation which will give you a clear idea. So this is plate number 1 and this is plate number 2. Plate number 1, as I said, that it is hot plate H, which is at the temperature of T1 Kelvin, and that value has been given as 800. And plate 2, which is usually taken as T2 Kelvin, and here its temperature has been given as some 500 Kelvin. And the emissivities between the two plates were also been given as epsilon 1 and epsilon 2, right? Okay. Now, as I said in the previous video, that when two bodies try to interact by radiative mode of heat transfer, definitely there will be some resistance associated, and already in the previous video we have seen that the electrical resistance will be represented as voltage difference by flowing quantity, which is current, right? So in the similar fashion, we can also represent your current I, which is a flowing quantity, as voltage divided by resistance, right? Similarly, we also have seen about the thermal resistance as temperature difference divided by the flowing quantity, which is heat. So your Q can be represented as delta T by R, right? Okay. Generally, the resistance will be represented like this. The total resistance will be 1 by 1 minus emissivity 1 by A1 emissivity 1. For those who have attended the previous class, they would understand that this is the surface resistance. Plus, there will also be some space resistance which will be taken into account, right? Which is 1 by A1F12. Because you know that plate 1 is the one which is going to radiate and that is going to reach plate 2, and it is A1, and shape factor or view factor or configuration factor between the two plates plus 1 minus emissivity 2 by A2 emissivity 2, right? and this is the surface resistance which is been present over here near to the second plate. Now as far as any plate problem is considered, you yourself has to come to a conclusion that the area of the two plates A1 and A2 will be taken as 1 meter square, and you can even check out with the options given here that it is per meter square, right? Per meter square in the sense it is 1 meter square, so your area terms can be neglected. And also one more thing, if you try to consider the first plate alone, so the fraction of heat leaving from the first plate can either fall on the same plate or it could reach the second plate, and the sum of the probability should be equal to 1. But since it is being flat, I can say that F11 will be equal to 0, which automatically indicates that all the heat which is leaving the first surface should definitely fall on the second surface, because you are getting the answer as 1. So view factor or geometry factor doesn't come into play when two parallel plates gets interacted by radiative mode of heat transfer, right? So this you have to understand. So applying the same, will be able to get the answer for this particular question. So these are all the data which has been given once again. T1 800 Kelvin, T2 500 Kelvin, epsilon 1 0.8 and epsilon 2 0.6. And as I said that your Q can be represented as delta T, and here according to Stefan Boltzman law, you know that it is T1 power 4 minus T2 power 4, which will be equivalent to your delta T. And also remember to include your Stefan Boltzman constant divided by the resistance term. And in the resistance term, as I said that shape factor won't come into play when two parallel plates get interacted with each other, and you will be able to substitute the values of your emissivity of the first plate and second plate, and you know the Stefan Boltzman constant, and you know the temperature T1 and T2, and try to simplify. You'll be able to get the answer in watts per meter square, and after getting this answer, try to divide it by 1000. You will be able to get the answer in kilowatt per meter square. So the answer which I am getting for this particular problem is 10.26 kilowatts per meter square. And if you try to check out, so it is option B. So option B is the correct answer, right? So try solving this problem, understand the problem, read the problem completely, and try to convert that into a diagrammatic representation so that you will be able to answer the problem in a very quick manner, right? So we'll do one more problem in this video, and this question was also been asked in the same year 1994. So you can see that if you are thorough with the heat transfer radiation part, you will be able to answer few such questions which has been asked in the same year. So here is the question: long semicircular duct is shown in the given figure. What is the shape factor F22 for this case, right? And you have been given with four options: option A 1.36, option B 0.73, option C 0.50, and option D 0.36. So it is a long semicircular duct. So semicircular, you know, and it is clearly mentioned that this flat portion is your first surface, whose area is A1, and this dome is being represented by the second surface. The semicircular portion, the curved portion, is being represented by the second surface, and whose area is actually A2, right? Okay, now you need to find out the shape factor F22, right? Okay, so we'll see how to apply this, but before even getting on to this problem, please do watch my previous problem where I have discussed the concept related to this particular type of problem, about the reciprocal theorem and about the summation rule. Summation rule was also been applied in the previous problem, so you can even try to apply the same thing and you'll be able to fetch the answer in a matter of time. So we'll just get into the solution part. So let us take the first surface and try to apply the summation rule, right? So summation rule states that the fraction of heat leaving from the first surface can either fall on the same surface or it can fall on the second surface, and its probability should be equal to 1. And since the first surface is actually flat, you can just see to the diagram, the first surface is actually flat, then there is no chance for the heat leaving from the same surface to fall on the same surface itself. So I can say that all the heat leaving from the first surface should definitely fall on the second surface. So F12 answer is actually equal to 1. Now try to compare the first surface and second surface, for which you have only one clue, which is your reciprocal theorem, which states that your A1, here it is 1, right? So you have to put F12 should be equal to A2 F21. So this is for thermal equilibrium, this relation holds good. So here you have to, you already know that your F12 answer is 1 from the previous step, right? Now, if you know the area of the two surfaces A1 and A2, you'll be able to find out the F21, right? Okay. So just refer to the diagram. You'll be able to see that the first surface is actually the flat portion, right? And its surface area will be simply length times diameter, right? Length into diameter. And because you know that it is of the diameter value, right? It is of diameter and it will have a certain length of L, right? If you can actually reproduce this for a length L, so it is L into D, and your second surface A2 will be simply equal to half the surface area of the cylinder, so it is pi d L by 2, right? So your A1 and A2 are known, so your F21 can be represented as A1 by A2 simply because F12 is already 1, right? So you can substitute your D into L and you can also substitute your pi dl by 2. So you'll be getting the answer as 2 by pi, and if you try to simplify you'll be getting, you know, the pi value is 3.14. If you try to simplify you'll be getting the answer as 0.637, right? Now try to apply the same summation rule for the second surface. For the second surface, if you try to apply the summation rule, fraction of heat leaving from the second surface can either fall on the first surface, plus fraction of heat leaving from the second surface can either fall on the same surface itself, and its value is equal to 1, right? And you are supposed to find out this answer, so you can bring this F21 to the other side of the equation, which you have found out in the previous step as 0.637. So upon simplification, you are getting the answer as 0.363. So if you get back to the options, so the nearest option is your option D because you are getting 0.363, right? So option D is the correct answer. Hope you might have understood this entire session of getting solved with the ESE problems. So far we have started with the gate problems, and also we have moved on to the ESE problems. And even in the future, I'll try to include as many problems as I can from the PSUs, and also from we can continue with the past gate question papers and ESE question papers, and also with relevance to the combined engineering services from the State Public Service Commission can also be included. So try solving these problems carefully, and if you have any doubts you can just post your doubts in your comment section. Let me address that in the next upcoming video. Hope you might have enjoyed this session. So if you like this video, please do subscribe, review, rate and recommend to your friends. We'll just catch up in the next video. Thank you. Bye.